Good morning, dear students. Today we are going to see about the solid mechanics course in the topic of thin cylinders. You know that the cylinders are mainly classified into thin cylinders and thick cylinders. So in the case of thin cylinder, how will you define it? The thin cylinders are the cylindrical shell which consists of the thickness and the diameter and the length, and the thickness is less than or equal to 1 by 15 to 1 by 20th of the diameter of the shell, then it is called as thin cylindrical shells or thin cylinders. But in the case of thick cylindrical shells, it is defined as the thickness is large compared to the thin cylindrical shell. So in the case of thin shell, you can take it as a 2 mm or 3 mm thickness or maximum of 5 mm thickness. But in the case of thick cylinders, thickness is definitely greater than 10 centimeter or 15 centimeter, or in the case of minimum, right, 40 mm to the 100 mm. But here we are going to see about only the thin cylindrical shells. So already I've told you the thin cylinders or cylindrical shell is of thickness is less compared to the diameter of the cylinders or the cylindrical shells. If you consider the thin cylindrical shell, mainly it consists of the two type of stresses, which is called as longitudinal stress and the tangential stress, or we can call it as a circumferential stress. So these are the two type of stresses induced in the thin cylindrical shells: longitudinal stress and the case of the lateral stress, which is called as circumferential stress. So in the case of thin cylindrical shell, the main criteria for the design is the thickness and the diameter of the thin cylindrical shell, which consists of the liquid or the volume of the component inside the thin cylindrical shell. At any case, you have to design carefully. The bursting should not occur or the cylinder should not fail. So in that case, you have to design the corresponding thickness. For that, you have to use the longitudinal stress and the circumferential stress. Hoop stress is also called as the circumferential stress. So the hoop stress is F suffix T, or you can call it as F suffix H or F1, which is equal to the pressure inside the cylindrical shell into the diameter of the cylindrical shell divided by 2 times the thickness. So it is measured in terms of Newton per square millimeter or MPa. But in the case of the longitudinal stress, it is nothing but is half of the circumferential stress or hoop stress. So if you are called as Ft is equal to Pd by 2T. So in that case of the longitudinal stress, it is longitudinal stress is denoted by F suffix L, or you can call it as F2. So that is equal to half of the Ft. So that means P into D divided by 4 times the thickness of the cylindrical shell. So in the case of P is equal to the inside fluid pressure, or the air pressure also can take it as, then D is the diameter of the cylindrical shell and T is the thickness of the cylindrical shell. So you have to design it, whichever is a greater one, you have to take design for the thickness. So in that case, both of the cylindrical as well as the hoop stress, the hoop stress is the maximum value, so you have to take it as a design for the design. So the thickness should be greater than or equal to PD by 2F, where F is the notation used for the allowable stress or the safe working stress. So the T thickness of the cylindrical shell should be greater than or equal to the inside fluid pressure of the cylindrical shell into the diameter of the cylinder divided by 2 times the working stress or the shear stress. So we have to design for the thickness. Once you are able to know the thickness of the shell, and you can go in for the volumetric changes, what will happen during the pressure inside the fluid. The volumetric strain can be taken as, right, epsilon v or E suffix v, that is equal to, right, E1 plus 2 sorry, E2 plus 2 E1. So E small E1 and E2 are the corresponding the hoop strain and the launch shear strain. So if you are able to calculate the launch shear strain and the hoop strain, so definitely you can go for the volumetric strain. E suffix V is equal to 2EL plus E2, where E1 is equal to the hoop stress and E2 is equal to the launch shear strain. So once you are able to calculate the strain, definitely you can go for what will be the maximum shear stress produced in the cylindrical shell. So in the case of cylindrical shell, tau max or Q max, that is the maximum shear stress produced, is equal to, so F1 minus F2 divided by 8 8T. So F1 and F2 are the corresponding the hoop stress and longitudinal stress, and T is the thickness. So from that you can able to calculate the hoop strain, and from that you can calculate the volumetric strain. So here you can able to design the thickness, diameter, and once you are fixing the length of the cylindrical shell, so you can able to design it for the either thickness or the diameter, on what are the hoop stresses and what are the longitudinal stresses can be able to withstand by the cylindrical shell. So in the next class, we are going to see about the practical problem using the thin cylinders or the thin cylindrical shell. Thank you very much for the patient listening, and goodbye. Thank you.